그럼 이번 강연은요, 양자 커넬에 대한 IBM의 최근 연구를 소개하고자 합니다. 크리스탄 템베 IBM 수석 연구원이 강연을 준비해 주셨는데요. 양자 커넬 기반 머신 러닝이라는 주제로 지금부터 영상으로 같이 만나보시죠.
Thank you very much for the opportunity to speak here. My name is Kristen Temi. I'm a research staff manager member and a manager of the quantum algorithms group at IBM Research. Today I'll be talking to you about our recent work on learning with quantum kernels. And so our goal here is basically to find places where you can naturally insert quantum mechanics and quantum mechanical methods into machine learning algorithms or classical machine learning algorithms. A particular focus of this work is basically that what we would like to have or to do is we'd like to look for algorithms that have the potential of running on current and near future devices, which means these are devices that are not fully fault tolerant, but will have progressively better coherence. And in order to think about such devices or think about such algorithms for those devices, you'll have to come to terms with the fact that the execution time or the time that you have to perform some algorithm is limited due to the decoherence effect that you have in quantum mechanical devices at that scale. And what that means is basically you have to sort of restrict yourself in terms of what kind of algorithms you are looking for. And one approach we can take basically is to say, well, okay, we accept the fact that there is a finite coherence time, and as such, there's a finite computation time and a finite depth of the circuit that we can effectively run. So we will only look for algorithms or applications that may fall within that particular coherence window, which means so the most natural candidate here is what we could do is we could look for algorithms that basically fall are short depth quantum circuits where the depth is specifically defined by how coherent your device is. And the goal of such an algorithm is then the very simple setup is basically you want to go and run some particular unitary circuit. And at the end of the circuit, you'd like to measure an observable. And what will happen is that this observable, despite the fact that you've restricted to a rather shallow depth circuit, is still going to be noisy. But the good thing about the setup is that there are certain methods you can apply that are not full error correction, but methods that we refer to as quantum error mitigation that can help you recover good and accurate expectation values. So our goal is basically in this entire approach is, okay, to look for algorithms that can be cast into the framework so that there's a potential that they can be run in the foreseeable future or devices. Right, and so a particular crucial interest of ours in this approach is basically what we're looking for in algorithms that are relevant to machine learning is are places where quantum mechanics might fit very naturally into machine learning problems, right? And so what happened is basically after a little bit of exploration, which I'll give a brief introduction to. We basically spiraled and started focusing on using quantum mechanics and using quantum mechanical state space as a stand-in for feature space for interesting learning problems. And that's what I'll talk to you about in this talk. And I'll give you a brief motivation for us. Say, let's start with the simplest setting, which is a binary supervised learning task. So we want to do a binary classification of, say, two classes in a supervised setting. And so sort of almost the textbook example, but that's a good point to start. And so what people frequently choose are neural networks or other things to actually accomplish that task classically. And one thing you could try is something that people have referred to as a quantum version of that classical neural network. People call that often a quantum neural network. And what I'll show you is basically that these quantum neural networks are essentially just linear classifiers in feature spaces that come from quantum mechanics, right? And so that the interesting part is actually mostly the feature mapping here. So how do those quantum neural networks work? So as you recall, so our setting is, okay, what we want to do is we want to have some sort of sense of a shallow depth circuit for this to work. And then we'd be able to do a measurement at the end. And based on that, you want to construct some sort of classifier, right? And so in quantum neural networks, so you could partition it into 4 stages, which is basically, okay, in the first stage, you choose to map the data somehow into the quantum computer. In that case, it could be a bunch of single qubit rotations that prepare a product state of single qubits. So imagine this is like a 5-pixel grayscale images that you're seeing here, where every pixel gets mapped to a single qubit and a rotation angle. And then you follow that with a very intricate quantum variational circuit. So a bunch of unitary gates that depend on some variational parameters that you can optimize and train. And in the end, you measure in the computational basis, you measure a binary function, which gives you either +1 or -1. And then once you have computed and estimated those expectation values, you do some thresholding and decide on whether you've seen more +1s or say more -1s. And in the histogram, and you threshold and say, well, if I've seen more +1s than -1s, I'm going to declare that this is a +1 outcome in my classifier. Okay, so what I'll show you, this is something that people consider quite frequently in the literature, right? At the moment on a more intricate setting, but that's essentially a high level description. And what I'll show you is basically that those things are essentially just related to linear threshold function and linear classifiers in a interesting quantum feature space. So allow me to basically, for 2 minutes, review classical support vector machines. I assume everybody at this conference is very much familiar with this, but allow me the small recap so I can pinpoint exactly to where the quantum stuff enters, right? So what's the goal here? Yeah, we're given 2 sets, left, right. We want to separate them, and the simplest thing that you could do is sort of divide them by a line. Left is +1, right is -1, or the other way around. And there's multiple lines we could draw, and of course we would like to have the line that has the largest margin relative to those 2 sets and still satisfies these the constraints. Let's make it hard for simplicity. And our classifier is then simply a sign function of the inner product with this normal, essentially, of that hyperplane. A simple so a linear threshold function. Okay, so of course in the wilds the data isn't always that nice, and that's the whole point of actually using feature spaces. And so what you do is you choose to map data that is not so nice and that is not linearly separable. You choose to map it by nonlinear mapping into a higher dimensional space, in which you assume that data then will become separable, or at least within a soft margin sense, will have a good soft margin, right? And so that could, in principle, increase the dimension and so forth, and go to a very high dimensional space. So it becomes convenient to consider the dual optimization problem of that initially convex optimization problem that you have, which is then concave. And what you realize is that the only thing that essentially enters in this, where the feature map essentially enters in that dual optimization problems, is in terms of an inner product. And that inner product becomes a special name, and that's essentially the kernel function. Okay, so much for the recap. So what I'll show you now is that in principle, this very frequently used approach that people consider in the literature, so those quantum neural networks, essentially does the same thing, right? So what you can consider is basically, if you look at this thresholding rule that we have of the expectation value in the end, if you cleanly write it out in terms of what expectation value that corresponds to quantum mechanically, then you realize that, okay, you have this expectation value, the histogram, which is of this particular form, and the thresholding condition then translates to essentially a sign condition. That's what the decision function then does. But now it comes with an inner product with a quantum state that you've initially prepared. This is the feature map state, so the data loading stage that I was referring to. And then there's another component which is plays the role of the hyperplane, and that's essentially the rotated observable. And that observable is being rotated by that variational circuit. Okay, so no matter how complicated or intricate your variational circuit is in the end, what it effectively always does is basically just prepare some linear threshold function that separates those two classes that you've initially prepared with that feature map. Now, in that particular example that I gave you beforehand, you can now say, well, okay, if this is the feature map, what is the corresponding kernel? And you realize that essentially corresponds to the fidelity between two initially prepared states. And in the example that I gave beforehand, what you realize is that it's a tensor product of individual single qubit rotations that assume the role of that feature map. And since it's a tensor product, what you realize is that it's very, very easy to actually compute that kernel function, and you can pretty much compute that kernel function in linear time. So anything that quantum neural network has done, you could do classically and probably even better. So it becomes difficult to say, okay, why would you want to use a quantum computer for this? And the answer is, in that setting, using this particular feature map, you probably wouldn't, right? Because you can easily do everything, all those steps classically for those quantum neural networks. Okay. However, things start to become a lot more interesting if you ask the question, well, are there kernel functions then methods or procedures of loading data in some way that would give you some separation in some sense? So would you do that allow you to do something non-trivial on a quantum computer that you couldn't have done on a classical computer beforehand, right? And so the main focus then sort of shifts from worrying about quantum neural networks, worrying about variational circuits and so forth, to pretty much the question is, what actually is an interesting way of loading the data into the quantum computer, or basically what is an interesting quantum feature map? So as we talked about this earlier, there are of course trivial examples of feature maps. The three examples are, one example is, for instance, the product states that we talked about previously. There are certain, in the setting of bosonic modes, they're so-called coherent displacement operators, and those things give immediately rise to classical RBFs, radial basis functions. There's a little bit more, a slightly more advanced thing that comes from computational complexity within quantum mechanics, which are so-called IQP circuits. But all of these, they initially seem to be difficult, but the task is basically to estimate that expectation value for that fidelity. And it turns out that all these feature maps that in these three examples that I gave you, you can classically estimate that that expectation value up to an additive error. So the crucial point is, what we need are basically feature maps that are difficult to estimate on a classical computer up to an additive error, but easy to estimate on a quantum computer. So because these feature maps then, how do they present and how would you use them in an algorithm? Well, what you have is these feature maps are basically unitary circuit families that depend on the data that you want to prepare, right? So in the first case, it was just single qubit rotations, but there might be more complicated ones. And what the kernel then corresponds to is that you prepare the initial zero state, you evolve forward with a particular element of that feature map circuit family, UXI, you evolve backwards with UXJ, and then you count how many times you basically see zero. And that essentially, that transition amplitude of that circuit turns out to be a kernel, or a particular a quantum kernel. And you can basically, in a quantum computer, estimate this kernel on hardware, and then basically think of various algorithms where you could need such a quantum kernel, where you could insert them. The interesting thing here is basically is twofold. Number one, what you would like to have is a kernel that you don't have access to through classical means. So that basically is going to guide our future research and trying to find such kernels and make them practically relevant. And the next thing is, it's sort of funny that you're sort of exploiting a very natural feat of quantum mechanics, which is the Hilbert space that you have available there, that you use to describe your system, to stand in as a state space as a feature space for quantum for machine learning tasks. Okay, so but this is basically what what's going to set us on our way to basically start looking for interesting or relevant algorithms that fit into this near-term paradigm, because it's a very deliberately simple algorithm. You just have to come up with some unitary circuit family that is of interest to you, and implement and estimate this transition amplitude. And much of the learning after having implemented that kernel can be done by classical learners that now have access to a very powerful, potentially very powerful kernel function. So the first question that would come to mind is, okay, fine, there may be kernels which may be hard to estimate classically, but so what, right? So it doesn't necessarily mean that they may help you in some learning problem, right? But to show that this can be the case and that it's worthwhile to continue that, and to make sure that we're not doing something that are not looking for a learning problem that can either also be solved classically. What we've looked into is basically we've constructed a separating example that basically addresses set questions. So what we wanted to show in this paper, just called the rigorous and robust quantum speedup and supervised machine learning, is the following. So that there are classical data sets that you can construct, so a bunch of labeled bit strings, where it is exponentially hard for any classical learner to find the labeling rule. However, if you have some standard support vector machine algorithm that has access to one of those kernel functions, those quantum kernel functions, that learning problem becomes polynomially efficient, right? So in that case, this is one particular example that stands in as a separation that shows you that formally there are things you can do with quantum kernels and standard machine learning algorithms that you couldn't have done without that. And so what we do here is we resort to some cryptographic setting where basically we generate a artificial data set that is based, which borrows its hardness, or it's difficult to classify from the discrete logarithm problem. And we show that there are kernel functions that basically allow you to actually classify that data set very cleanly, right? So the interesting part is really that this is done by a kernel function, because a priori you know that a quantum computer should be able to solve the discrete logarithm problem based on Shor's factoring algorithm. But the interesting component here is that this happens for a particular kind of quantum kernel, right? And that becomes the binary learning problem then becomes easy classically while it is still hard quantum mechanically. So I won't go into the technical details of that, but I'll skip ahead to the next natural question, which is, okay, sure. Now you've gone and if you were to believe this, you've gone and constructed a learning problem for which you can formally prove that no classical learner can solve it. But it's not really an interesting or relevant learning problem because it's a very artificially constructed one relative to a data set for the discrete logarithm problem. So the question is, going from there, so how do we explore or how do we find relevant learning problems or problems for which this quantum kernel approach could be useful, right? And so what we've been doing then as of late was we looked into a particular family of quantum kernels that we refer to as covariant quantum kernels. And the idea here is to basically classify data where the data itself obeys some sort of a group structure. Okay. So before we dive right in, so what are examples? Why is this practically relevant? Examples are, for instance, if you would like to classify or learn permutations. So those are rankings which are rather important and relevant. There are other classes of examples where you look at cosets or homogeneous spaces and you want to have some learning problem on cosets or homogeneous spaces where you could envision that this learning approach might be relevant. And so how do we set those kernels up? Allow me to introduce them. Assume that you're giving, say, for instance, just elements from a group, i.e. permutations or some abelian group, if you like, and some labeling rule. And then we want to construct some sort of a kernel or a quantum feature mapping from that. Okay, and so how is that given? So suppose there exists some reference state, call it psi, that we refer to as sort of the fiducial state. And then we assume that we are given some unitary representation over that group. And what we would like to have is that this unitary representation can be efficiently implemented on a quantum computer. So both components, there should be some preparation circuit we'll call V that should be able to prepare that reference state. And the next component is there should be some group action that basically then later acts on V, on that state psi to prepare the actual feature state. So the feature state is then this projector. And as we said before, the kernel is then the overlap between, or the Hilbert-Schmidt inner product between those two states, which reduces for pure states to the fidelity. And you can see that the kernel that you're looking at is essentially this fidelity between psi forward evolved with one group element, backward element with the backward evolved with the other, and then count the transition amplitude, and so just simply counting the zeros, right? So that is the abstract high-level setting of what we refer to as a covariant quantum kernel, and the interesting part is now to find concrete realization of such kernels, right? And so the first question you may ask is, okay, sure, you defined that class of kernels, but is that an interesting family of kernels in the sense of, does it allow you to do things you can't do quantum mechanically? And what you can show is basically, what you can see pretty easily right away is that the initial problem that we used as a formal separation, so the problem that is relative to the discrete logarithm problem, the feature map that we ended up using and the kernel that we ended up using is specifically of that particular form. So in our case, the feature map that we would need to use to solve that problem turns out to be sort of a very uniform superposition over that generator for the discrete logarithm problem, and it assumes this form. And if you break it down into components, what you'll realize is that, okay, there is a representation that acts on the computational basis elements, which is basically the regular representation of the multiplicative group modular P, and then there's one fixed fiducial state which can be prepared in with a polynomial-sized quantum circuit, which is this psi, which is the sum over all those generators. And with these two components, so with the group action and then later with that fiducial state, what you realize and see is that, okay, with this problem, if you believe what I told you about the previous result, then you can solve a problem that is classically inaccessible. But it's kind of interesting to look at this, because what you realize with this with this particular example is also that this fiducial state, or this reference state, what you choose there is actually very, very important. So if you choose just a computational basis state instead of this very intricate and complicated fiducial state for the D-log problem, what happens is that the regular representation then acting only on this trivial state will lead to a kernel that is very easy to evaluate classically, because it's just the point measure, or the point difference between the two elements of that group, right? And so so there's a kernel that is going to give you a very, very poor classification, because it's just essentially the identity matrix, versus a kernel that gives you arbitrarily with polynomial effort good classification of that problem. So it's very important to choose that fiducial state wisely, and a lot of the difficulty basically comes in picking a good candidate for those fiducial states and for those learning problems. So there's various ways you can go about this, but say let's start out with a heuristic. And one heuristic we've chosen, and I'll show you an experiment shortly, is referred to as kernel alignment. Right, kernel alignment allows you to pick a particular kernel out of a family of kernels, and the goal here is to basically choose a kernel that gives you what you optimize in this in a weighted version of kernel alignment. What you're essentially trying to do is you optimize the upper bound on your generalization error in your classifier. And now what you could optimize over is a particular a set of trial states that you can prepare with some relative shallow depth circuit, and find a good candidate that works well for a given set of data. Okay, and so that's something we'll show I'll show an experiment of shortly. But maybe let's choose one stand-in learning problem that might be interesting to us, right? And so we call this generalization that learning problem is in labeling cosets with error. And so we are assuming here we have some given group, and there's sort of a subgroup to this group. And so we choose two cosets from that group, label one coset as +1, label the other coset as -1, add some noise to both of those cosets. And then we use the representation of the initially larger group to act on some fiducial state. And this is going to be our feature map, and this is going to be our stand-in learning problem to explore this a bit further. And so what turns out to be actually what we believe turns out to be a pretty good candidate for a fiducial state is basically a state that happens to be invariant under the group action of the subgroup, but obviously not the group action of the whole group, right? And so what happens then is basically that this classifier, that feature map basically cleans up the data and makes it easily separable by having basically mapping to both cosets to two individual states, which should become easily distinguishable. But so if you add noise and you can add extra errors and perturbation, then it becomes actually an interesting learning problem by itself. But you should still be able to retain an easy classification based on the fact that you've chosen that as a reference state. Okay, and so just to consider a really trivial example, so this is sort of a single qubit coset, and there you can visualize things quite neatly on the blocksphere. And what you see is basically we take sort of just standard single qubit rotations as our larger group, and then we pick a particular subgroup, which is like a cyclic group of 3 elements. And if we choose a poor reference state, so some computational basis state that is sort of just the 0, then what we end up with is we essentially get the cyclic group action on that thing as 2 triangles. And you can see that this is definitely not going to be linearly separable. However, if we choose a very convenient representation, which is basically then, say in this case, the plus state, what you realize is that basically that group action becomes trivial. The 0 state in that case, the group action becomes trivial, and things become extremely easily separable. And so what we care about is basically to construct or to look at an example where something like this happens sort of in the wild. So we're not quite there yet, but what we care about is actually a larger scale experiment where we could observe such an effect, and so we can continue this a bit to explore this a bit further. And so what we do is basically a setup that is very natural to our physical hardware that we have on our device, and I'll show that in a bit. And so what we do is basically we take the group of single qubit rotations on every individual qubit, and as a subgroup we take a stabilizer subgroup, which is a subgroup of the Pauli group, which has the property that it is abelian and stabilizes a particular graph state. So it allows you to actually find a good representative of that fiducial state psi. So what we do is we basically choose randomly 2 elements from the tensor product group of single qubit rotations, choose the graph state stabilizers, then basically pick elements from that group and then perturb them. And that's going to generate our fake data set that we'd like to classify and experiment. And we'll see on how that does. So the fiducial state that we then choose is going to be a state that has first going to prepare a bunch of single qubit rotations, variational parameters, and then basically has some CZ interactions along the coupling graph of the chip. And when we choose that fiducial state, we know that in principle there is a choice in the parameter landscape that represents that really good fiducial state, of which we believe to be a very good fiducial state that should lead to very high classification accuracy. And we can start our entire optimization in the kernel alignment procedure with an initial state that is rather far from said graph state, and try to explore whether upon providing that circuit family, we are able to find a said good candidate state. And so in the experimental setup, this looks in the following way. So we have a 27 qubit chip. We do this experiment on 27 qubits. We have the red box corresponding to a unitary circuit that prepares the traditional trial states. The single qubit rotations we're considering here correspond to the group representations of our tensor product single qubit group. And so this entire transition amplitude of that circuit corresponds to this, the quantum kernel that we're considering, defined on that 27 qubit chip. Okay, so what happens now if we start out? We choose initially poor, we generate data, we look at this, we know the data is generated in such a way that in principle it should be classifiable to 100%. And what we do now is we have, we let our kernel alignment algorithm run. And what you can see is with initially poor choice of the parameters that we have available, and then basically, however, optimize the, in a min-max optimization problem, perform kernel alignment, improving the, hopefully the upper bound. What you can see is basically in the progress of this optimization procedure, the kernel sort of aligns itself in such a way that the respective feature classes become much more apparent, and the corresponding cost function, so the training error in that case, basically goes down, reduces. And what you can see is basically that at the same time, the classification error, so the test error, reduces as well, and we achieve test accuracies approaching unity, as should be the case if we know that in a certain setting the data has to be separable, and you should have a very, very good classifier. So that the interesting thing is, in that setting, this is of course again an artificial example. However, to conclude, sorry. However, the interesting part there is basically that this example represents quite a few natural applications that one could start exploring this way. And we mostly do and are interested in this experiment and at those scales to actually see whether these ideas carry weight and work out in actual experiment. So I think with that, I'm very well at the end of my talk.